Hello physics students. Welcome to the Snell's Law Lab. Now at this point, you should have already printed out pages 3 and 4 of the document included in the Google Classroom stream. This is where you're going to record your data, analyze it, and also answer questions. Pages 1 and 2 are instructions, so you don't need to print those out unless you want to. Now the purpose of this experiment, stated right on page 1 of the lab sheet, is to determine the index of refraction of water. But we already know the index of refraction of water. We could look it up on our Regents reference table. Right here, near the bottom of the table of indices of refraction, you could see water's index 1.33. But of course, what we're going to do is do an experiment and see if we could generate that value. Probably we won't get exactly 1.33, we'll get something a little close, but a little off, and then we'll do a percent error. So that's the experiment. So why don't you come a little closer, and I'll show you how we collect the data, and I'll guide you through its analysis. So the equipment that I have to achieve the purpose of this lab is a special plastic semicircular dish that looks like this. I can't pick this one up because it's filled to the top with water. So it's filled with water. There's the water that's going to refract our light for our experiment. It's set on a piece of polar graph paper that will make measuring the angles coming in and going out of this surface easy to measure because we could just use the graph paper instead of a protractor. I also have a light box, which I mentioned earlier in the topics, and you've seen it. Basically has a little slit at the end here that's going to produce a nice narrow beam. So let's begin. The first ray I will send in here will be coming in like this on this surface, this flat surface. This is the incident ray. Theta 1 is the measurement of the angle of this ray. If we're in class, I would ask you, what is theta 1? And I would wait for people to answer. A lot of people would answer 90 degrees. Here's the surface. It's coming in like this, 90 degrees to the surface. That's incorrect. Remember, all angles in optics are measured to the normal. And the normal is perpendicular to the surface. It would be something like that. So what's the angle between the normal, my pencil, and that ray? Well, if I had it perfectly aligned, they'd be one on top of each other. In other words, there is no angle difference between the two. So this angle is actually 0 degrees because it's coming on the normal. Furthermore, the angle in the water is, the ray comes out also on the normal. Here's a surface, there's a normal. So the angle here, theta 2, is also 0 degrees. 0 degrees in the air, 0 degrees in the water. So I'm going to transfer that to my data table. Okay, there it is. Now, your data table is going to look a little bit different, because what I'm going to do is I'm going to blank out all these theta 1s, because everyone I want to have their own data. So in order to allow me to make more fluctuation, you'll be assigned both theta 1s and theta 2s. So you're going to get theta 1 and theta 2 off the data table, and you're going to record off the document in the Google stream, and you're going to record them right there. So the next thing that I'm going to do is now I'm going to measure another ray. So I'm going to take this and turn this so that theta 1 is, in my case, 10 degrees. So again, here's the normal. I count over 10 little boxes over for 10 degrees theta 1. And I see that theta 2 is not 10 degrees. What it is, if I use the graph paper to count, it's, well, here's 5, 6.5 looks like approximately. Let me just make sure everything's lined up. A little out of alignment. Okay, that changed it a little bit. 7.5 degrees what theta 2 is. So 10 and 7.5. And, oh, I didn't have the degree symbol, so I'll add it. So go ahead in the Google stream and find your second piece of data. Everyone's going to have 0, 0, but the second piece of data, find theta 1 and theta 2, record them into your data table now. All right, next thing. What I'm going to do is now change this to the second angle, which in my case is 10 degrees. So I go like this. there. This is 20 degrees from the normal. Okay, so what is the angle now after going through the water and refracting at this surface? Well, here's 0, 10. So to me, it looks like it's about 15 degrees is my theta 2. So I'm going to write that down. But again, you're going to go into the Google Stream. Go ahead and do that now and find your second angle, theta 1, second entry for, or actually the third, 1, 2, 3. So for theta 1 and theta 2, get those from the Google Stream and copy them now. Okay, I'm going to go up another angle. So in my case, I just did 20 degrees. I'll do 30. There it is. And then the ray coming out of the water. Now you could definitely notice the light bending. But here's 0 degrees. The normal's right here. 10, 20, 21.7 is what I get for my measurement. So you go ahead and look up in the document the data for your fourth angle, theta 1 and theta 2. All right, now I'm going to increase. I'm going to go to 40 degrees, which is going to be right here. Oops. Okay, 40 degrees here, 10, 20, 30, 40 right here, this angle. And over here, starting 0 normal here, 10, 25, 26, 27, 28.3 degrees is what I get for my angle, 28.3. So go ahead into the Google sheet that I have in the stream and get your angle, looks like your fifth angle, theta 1 and theta 2. Get both those angles now. And now what I'm going to do is go to 50 degrees, somewhere around here. And my angle here is 10, 20, 30, 34.5 degrees. So I'll write that down. So again, go into the Google Stream, get from that document, get your sixth pair of angles here and record them now. Okay, now I'm going to go to 70 or 60 degrees. So 10, 20, 30, 40, 50, 60 degrees will be right here. Okay, and my angle over here is 10, 20, 30, looks like a little bit less than 40, maybe 39.5 is the angle right there. I'll write that down. So go ahead into the document that I uploaded and get your seventh pair of angles, theta 1 and theta 2, and record them into your data table now. Okay, and then 70 degrees, I'll increase this angle even more. All right, so my angle here, 70 degrees there, and then here is 10, 20, 30, 40, 43.5 is approximately my second angle, theta 2. So go into that document that includes the data and record your eighth pair of data points for theta 1 and theta 2. Go ahead and do that now. Okay, and one more piece of data, 80 degrees. Okay, looks pretty close. This one's pretty hard to see over here, but looks like when I tilt the paper up, it becomes a little easier to see. So 80 degrees here from the normal. This is counting over 10, 20, 30, 40, about 45 degrees is that second angle theta 2. Yeah, that didn't change it much. Okay, so get your last pair of data points, theta 1 and theta 2, from the document in the Google Stream now. All right, so that's the data. What I'm going to do is pause the filming so I could clear this out of the way so that I could show you how and guide you through the analysis. Next, we're going to plot the data. But here's the problem. Snell's law has sign in it. It has sign on both sides of the equation. So if we were to just plot these thetas here, we'd get a curve on our graph here. But there's a little trick. You could actually make this data a straight line relationship if you calculate the sines of each of the angles and plot sine and sine on the axis. You'll see a straight line. So what we're going to do before we begin plotting is just calculate the sines of these angles. For example, this column is sine theta 1. So what we would do is do sine of 0, and make sure your calculator is in degree mode, not radian mode. And when you hit enter, you get 0. So sine of 0 is 0. And then next what we're going to do is calculate the sine of theta 2. Well, sine of 0 is 0, so I don't need to punch that on my calculator again. But the next thing we're going to put over here is the sine of 10 degrees. So if I hit sine 10, what I get is 0.174. So I will write that here. And there's no units to what comes out of the sine function. So I write that here. And then this, I'm going to take the sine of 7.5. And I get 0.131. So I'll write that here. And next, I'm going to take the sine of 20 degrees. Sine 20, that's sine theta 1, and that gives me 0.342. But of course, you have your own numbers, but you're taking the sine of this column here, 0.342. And then here, the sine of 15 degrees, but of course, whatever value you have for the third theta 2. So mine's 15, and I get 0.259. So I'm not going to do all of these because yours are all different anyway, but go ahead and do that. Calculate the sine of all of these and fill in this column here. Then calculate the sine of all of these and fill in the column here. So go ahead and do that now. Okay, the next thing that we're going to do is we're going to now, as I said, plot these two columns. This will be on the x-axis, and this will be on the y-axis. So fill in the columns here, the titles, right? We got to label these. There's no units, so you're just going to put sine theta 1 here, sine theta 2 here, and make sure there's a title to the graph. You could call it Snell's Law Lab or something like that. It's up to you. And then plot your data points. And then set up your axes. Basically, you'll see that, well, I won't tell you. You figure out what you need to scale these axes by to capture all your data. So go ahead, label your axes, label the values and a title. Go ahead and do that now. All right, the next thing we're going to do is plot our points. So for example, 0, 0 is a point, and then mine is 0.17, so the x value is 0.174. Maybe it's somewhere here. I don't know. I didn't scale my axis. And then 0.13, maybe it's somewhere around here. So I put a point like this. Same here. I go 0.34, maybe it's somewhere around here. And then 0.259, maybe it's somewhere around here. So I put my point right there. So you're basically going to do like points like this. Okay, so go ahead and carefully plot your points now. All right, so the next thing that we have to do is once we get a straight line is we have to draw a best fit line. I forgot a ruler, But what I can do is I could use, I suppose, this clunky plastic block, but you're going to take a ruler and just set it down, hold it tightly in the right spot, and do your best to draw a nice best fit line. Make it go through the origin, and then again, we've practiced best fit lines a lot, so you kind of know the idea of how to do it, but make sure it goes the whole scale of the, or whole, from one side of the graph to the other. So go ahead and draw your best fit line now. All right, what we're going to do is calculate the slope of that line now. So, let's see, somewhere around here. Okay, so what we're going to do is we always begin with an equation. So write an equation for how you calculate slope. Then you're going to plug in numbers, and then you're going to put the answer. And there may or may not be units. I'll put units question mark. You decide if there are units. If there are, then what they are. But before I stop for a pause, I just want to remind you, you're graded for the accuracy on the slope. So one thing, you're not using any of your data points in your slope calculation. If you're taking any values here or any points like this, you're going to lose credit. The other thing is, you want to pick points far apart, like don't do the slope of these 2 points. So basically, no data points, you pick 2 new points on the best fit line. Don't pick points close together like that. That magnifies the error. What you want to do is pick a point near the beginning and a point near the end and find the change in y and change in x and calculate the slope from those. And then you'll have minimized the error in the experiment. So go ahead, and do that calculation now right here. Calculate the slope. All right, so the next thing, from this slope, the instructions say calculate from this slope the index of refraction. And I'll just give you a hint. It's either equal to the slope or it's equal to 1 over the slope. Remember, water's is 1.33. So try it either way. But when you figure out which of these it is, make sure you write a formula, one of these, then a substitution, and then an answer for the index. I'll put W for water. So go ahead and figure out which of these formulas is appropriate, then use the slope in one of those formulas to calculate the index of water. Go ahead and do that now. All right, so maybe I got 1.38 or something. I don't know, making up a number. You know, it's not going to be perfect, 1.33. But the next thing that we're going to do is calculate a percent error with the value that you got and the accepted value. So that's what this big box is here for the percent error. So go ahead and maybe I'll write the formula. Percent error equals theory minus experiment over the theory, or maybe accepted if you want. So this is 1.33. This is what you got in the experiment. So go ahead and calculate percent error now. All right, questions. This one's a little tricky. Students often have trouble with it, but the question is, why does no refraction occur at the curved edge of the dish? So let me just grab the instructions. So here's a picture of the, or diagram of the setup. Okay, so we see refraction here. The light bent, right? Instead of going like this, it bent. But why doesn't it bend here? Notice it goes in this direction towards this surface, and then it continues that same direction. It's not like it went like that or like that. It did not bend here. And why didn't it bend? Well, what I the hint I give is that if you were to just circle this and erase everything else away and look at that surface, forget about the lab. Why doesn't the light bend here? Think about what theta 1 is and then what theta 2 must be based on theta 1 as it's coming in and going from the water to the air here. So go ahead and answer that question now based on what you see here. Answer right there. Okay, the next thing. The graph below experiments data you generated in this lab. Sketch a line that would represent the data for an index in which the dish was filled with a liquid with an index of refraction greater than the index of water. So to answer this, it's going to be like this or like this, one or the other, a straight line. And to answer this, think about Snell's law, n1 sine theta 1, and think that this is the air that's down here. And then think of what happens if this index gets bigger. What's going to happen to all the y values on this graph? Are they going to shift up or down? And then draw the appropriate line based on that question. So go ahead and answer that now. The last question, you just calculate the critical angle for the water-air interface. So if you're not sure how to do this, go back to the video lesson on critical angle and see how that's done, and then go ahead and calculate, and in the end you'll have theta critical over here, some answer. So go ahead and calculate that now. So that was the Snell's Law Lab. I hope you enjoyed the experiment. I hope you enjoyed the video. I'll see you in the next physics video.